If you deploy a frozen agent in production, you quickly run into a ceiling. The policy is fixed. It cannot update its own weights. When it encounters a failure mode, like looping on a bad SQL query, it repeats the same mistake until the session times out. The standard fix requires manual intervention. A human engineer has to read the failure traces and hand code a specific heuristic, prompt adjustment, or recovery rule into the agent's harness to prevent that specific loop from happening again. Harness-R1 replaces that human bottleneck with a meta-harness architecture. Instead of hard-coding rules, the system trains a secondary model to read the failure traces and autonomously write the code for the overlay harness. This divides the system into two distinct actors. The target agent is a frozen React policy executing tasks on a benchmark. The second is the engineer model, trained specifically to observe the target and write Python code to correct its path. Allowing a large language model to autonomously write Python code that immediately executes inside a training loop is highly dangerous. It exposes the system to a severe OWASP LLM06 vulnerability, executing untrusted code with potential access to the local environment. Harness-R1 runs a strict 6-stage pipeline. The top loop's engineer model generates code, which is heavily sandboxed before reaching the bottom loop's frozen target. The engineer is then updated based on the target's empirical performance. Success earns a reward. Transitioning an execution harness from a static, human-authored file into a dynamically learned surface requires mathematically locking down how that code is executed. Stage 1 of the pipeline establishes the baseline. The frozen target agent is deployed on a benchmark like WebShop or ElfWorld for a fixed-length rollout. The agent attempts the task, and its failures are recorded. Those raw failures are then assembled into this failure packet. To prevent the engineer model from cheating the reward signal, the target's true answers are structurally scrubbed from the record. The packet is also capped by a strict maximum character limit. If the failure trajectory exceeds that limit, it is simply truncated. The system relies entirely on hard context boundaries, rather than using a retrieval mechanism or a summarizer. In Stage 2, this sanitized and truncated failure packet is injected directly into the engineer model's prompt, triggering the generation phase. The engineer operates under a strict think-then-patch protocol. It gets exactly one turn. There is no iterative reasoning, and it cannot call external tools to test its ideas. It must process the packet and emit a solution in a single completion call. That single completion starts with a reasoning block. The contract demands 4 specific components. The model must identify the recurring failure, pinpoint the sub-goal state where the agent is stuck, assign a specific lifecycle hook to own the fix, and state the regression risk of the proposed code. If the resulting code fails structural validation, the engineer doesn't get infinite retries. It is bounded by an explicit repair attempts counter. If the code is rejected, a deny and continue loop feeds the error back for a correction, but cuts off entirely if the counter maxes out. Combining context truncation with a hard limit on single-turn generation prevents the engineer from burning resources in unbounded hallucination loops. Stage 3 dictates how the engineer applies its fix. It emits a structured JSON patch. In the current version, that vocabulary is restricted exclusively to one action: add code hook. The patch must target one of 4 specific lifecycle attachment points in the agent's runtime: on init for task construction, make pre-hint before an action, on before action to intercept a decision, or on post-step to evaluate the environment's response. Consider a specific case. The frozen target agent keeps searching the exact same WebShop query, burning its maximum allotted turns without making progress. The engineer reads the failure packet and proposes a fix, a Python script bound to the on-post-step hook. The script will monitor the agent's actions, detect the duplicate search, and inject a hint telling the agent to stop repeating itself. But before that Python script can execute, it must pass through Stage 4, the abstract syntax tree sandbox. This grid is the load-bearing safety seam of the entire architecture. Compile hook analyzes the code structure and outright denies basic operations like while loops and lambda functions. Notice the rejection of the import statement. The sandbox completely isolates the hook from networks and local file systems. It also rewrites Python built-ins down to a strict 24-name allow list. Functions allowing arbitrary execution, like eval, exec, and open, are stripped entirely. The restrictions continue at runtime. The execution environment enforces a hard wall clock timeout and caps the exact number of lines the generated code is allowed to execute. If the engineer writes a script that triggers a timeout or throws an exception, the system initiates a fail-downgrade to none. The crash is absorbed, and the hook simply becomes a harmless no-op. The target agent continues unaffected. By structurally blocking dangerous operations, isolating the environment, and absorbing execution failures, the AST-sandbox removes the threat of arbitrary code execution. It makes the inner loop safe to train. In Stage 4B, those successfully compiled hooks are wired directly into the frozen agent's active chat session. They form a tight envelope around the target model's inference call. Make pre-hint nudges the model. On-before action acts as a gatekeeper, and on-post step verifies the result of the environment step. Let's look at the web shop duplicate search fix. Because the sandbox forbids while loops, the engineer builds a cyclical state machine. It uses an episodic scratchpad called NB to count scene searches turn by turn, firing an inject hint effect when the count crosses a threshold. The restriction on control flow is deliberate. It forces the engineer to track loop detection as folded state across multiple on-post step invocations, keeping the execution highly predictable. Furthermore, the hooks are only handed a deep-copied view of the agent's context. Even if the engineer's code attempts to mutate the state variables, it only alters its own isolated copy. The only way the code can influence the target is by returning a specific effect. Each hook operates under a strict allow list. On-before action can only block, rewrite, or force an action. Anything outside those boundaries is discarded. Forcing the engineer to use step-by-step state tracking, isolating its memory access, and restricting its outputs guarantees the overlay code can guide the target, but cannot hijack the runtime. Stage 5 evaluates the impact of the newly installed code hook to determine the reward. Harness-R1 completely rejects the standard practice of using an LLM as a judge to grade the patch. Instead, it relies on outcome-grounded verification. It takes the frozen target agent, installs the new overlay, reruns it through the exact same environment, and measures the empirical success rate. If the system simply reruns the agent, the new code could hack the reward by selecting an easier task. To stop that, an identity protocol hashes specific benchmark parameters, like the web shop manifest. The patched and baseline runs must match this hash, guaranteeing identical tasks. Once the run is verified, the system subtracts the baseline average reward from the patched average reward. This yields a continuous numerical metric, the delta average reward. Moving to Stage 6, that precise numerical delta is passed to the trainer. The system uses group relative policy optimization. The continuous delta acts as the group baseline advantage signal, which directly updates the engineer model's weights. Because rerunning the target agent on every sample is computationally expensive, the system writes the reward to a semantic cache. The cache is keyed by a context hash of the patch itself. If any parameter changes, the cache invalidates, preventing stale rewards from polluting the training data. Cryptographically enforcing the task parameters ensures the engineer is rewarded solely for improving the agent's behavior, making metric hacking impossible. The entire 6-stage flow is supported by 3 memory tiers. The episodic scratchpad manages in-run state, dropping data when sessions end. The semantic cache holds on-disk reward data, invalidated by content hash to stop zombie memory. Finally, procedural weights absorb the successful policy. The target agent retains 0 memory of its own outside of the immediate chat session. Every piece of persistent logic is managed entirely by the meta-harness. But the architecture does have one critical limitation preventing immediate enterprise deployment. There is absolutely no human approval gate between the engineer emitting the patch and the target agent executing it. This missing approval step is acceptable for sandboxed benchmark research. The target cannot access external networks, and the built-in structural constraints prevent the agent from regressing its already successful behavior. To push this to a live production environment, the pipeline requires an automated gatekeeper. The framework demands a 2-stage classify and deny classifier to intercept the patches before execution. By strictly bounding the context window, locking down the abstract syntax tree, and enforcing deterministic evaluation, Harness-R1 proves that the execution layer surrounding an AI agent no longer needs to be a static file. It can be a safely learned, autonomously updating system.